dig through the research, the sources, and pull out the key insights for you. Think of it as your shortcut to getting genuinely informed. Today, we're tackling something really fascinating in material science, where it's less about discovering quantum properties and more about actually, well, engineering them. The topic is twistronics. We're going to explore how just twisting these incredibly thin materials can kind of magically unlock totally new quantum behaviors. Some are quite bizarre, actually.
That's right. And what's so exciting is that it feels like we're really entering an era of, you could say, materials by design.
Yeah.
We're primarily talking about two-dimensional materials here, things like graphene, of course, but also others called transition metal dichalcogenides, or TMDs for short. And the key idea is how this really simple geometric tweak, just a tiny rotation between layers, completely changes their quantum world.
Okay, so our mission for this deep dive, we'll lay out the basic materials first, understand what they are. Then we'll look at the geometric trick, this twisting that makes everything happen. After that, we'll get into the big discoveries, especially with twisted graphene, which really kick things off. Then we'll explore what's happening with these other materials, the TMDs, and finally, take a look ahead. So, are you ready to see what quantum powers a simple twist can unleash? Let's unpack this. To really get twistronics, we need to start with the basics. These 2D van der Waals materials, what are they fundamentally? We're talking atom-thin layers, right? Just one or maybe a few atoms thick. And their properties are just wildly different from the same material in bulk form.
Exactly. And the poster child for 2D materials is graphene. It's just a single layer of carbon atoms arranged in that familiar honeycomb pattern. It has some truly exceptional intrinsic properties. Electrons move incredibly fast in it. The mobility is huge, up to maybe 250,000 centimeter Ds. And plus, its thermal conductivity is astonishing, around 5,000 WMK, much better than copper or diamond. And it's nearly perfectly transparent to light. Quantum mechanically, it's what we call a zero-gap semi-metal. Its electrons behave like massless Dirac fermions near specific points in its energy structure, the Dirac points. This means they move very fast, almost like light within the material, and don't scatter easily. But that lack of an energy gap, that's a big hurdle for traditional electronics because you need that gap to turn transistors off effectively.
Right, the off-switch problem. And that's where these other materials, the PMDs, come into play as an alternative or maybe used alongside graphene.
Precisely. Transition metal dichalcogenides, TMDs, they have a formula like mx euros, M being a metal like molybdenum or tungsten, X being sulfur, selenium, tellurium, and they offer some really key advantages over graphene for certain things. Crucially, they do have an intrinsic band gap, and it's tunable. Even more interestingly, it changes from indirect in the bulk material to direct when you get down to a single monolayer. That direct gap is vital for interacting efficiently with light-think LEDs, photodetectors, solar cells. And another big thing with TMDs is strong spin-orbit coupling, SOC, much stronger than in graphene. This leads to a fascinating property called spin valley locking. Essentially, an electron's spin, its intrinsic magnetic moment, gets tied to its momentum, specifically which valley in the band structure it occupies. You can think of it like the electron having an internal compass that depends on its direction of travel. This is really the foundation for newer ideas like spintronics and valleytronics, using spin and valley information for computing.
Okay, so we have graphene, the speedy semi-metal, and TMDs, the light-loving semiconductors with this spin valley thing. How do we put them together? This sounds like the heterostructures part.
Exactly. Van der Waals heterostructures, this is the revolutionary fabrication idea. Because these 2D layers interact via weak Van der Waals forces, you can stack different ones together almost like atomic scale Lego. You can put metallic graphene next to semiconducting TMDs, next to insulating layers like hexagonal boron nitride or HBN. And critically, you don't need the crystal lattices to match up perfectly, which is a huge constraint in traditional materials growth. The stacking capability is, well, it's the fundamental platform that makes all of Twistronics possible.
Okay, got the building blocks. Now for the twist. The magic, as you called it. This Moiré superlattice idea. What is that, physically?
It's basically a geometric interference pattern. Imagine laying two identical repeating patterns, like two sheets of graph paper, on top of each other. If you rotate one slightly, you see this larger scale pattern emerge, right? That's a Moiré pattern. In 2D materials, when you stack two layers with a tiny twist angle, say S, this Moiré pattern creates a new, much larger periodic structure, the superlattice. Its wavelength is roughly given by S, where H is a sin, where AK is the original lattice constant. Now, for very small angles, like the famous magic angle near 1.1 degrees in graphene, this Moiré wavelength becomes huge, tens of nanometers. A single unit cell of this Moiré pattern can contain over 10,000 atoms.
10,000 atoms in
Yeah.
one new unit cell. That's massive on the atomic scale. So what does that do to the electrons living in these layers?
Ah, that's the core question. This giant Moiré pattern isn't just visual. It imposes a powerful, slowly varying periodic potential on the electrons. Think about how the atoms are aligned locally. In some regions of the Moiré cell, the lattices are perfectly aligned, AA stacking. In others, they're offset, ABBA stacking, and it varies smoothly between these configurations. This variation modulates how easily electrons can tunnel or hybridize between the layers. This Moiré potential is the central physical mechanism. It forces the original electronic bands of the individual layers to fold up into a new, much smaller energy landscape, a mini Brillouin zone. It fundamentally reconstructs the electronic states. You can almost think of it as creating a periodic array of quantum wells or traps for the electrons. It forms a lattice of what people sometimes call artificial atoms.
Artificial atoms, wow. And this wasn't just stumbled upon experimentally. There's theory predicting this. You mentioned Bistritzer and McDonald.
Absolutely. A really seminal theoretical paper by Bistritzer and McDonald back in 2011 used what's called a continuum model, a simplified but powerful approach. They predicted that for twisted bilayer graphene at specific magic angles, the coupling between layers would cause the electron velocity near the Fermi level to vanish. Zero velocity means the energy bands become extremely flat. That was the key prediction.
Flat bands. Okay,
Okay.
we'll definitely come back to that. But first, making these things. It sounds incredibly fiddly. How do researchers actually achieve that precise twist angle in the lab?
It is fiddly, you're right. The breakthrough technique, the one that really enabled the magic angle discoveries, is often called tear and stack, or sometimes cut and stack. The basic idea is you exfoliate a flake of the 2D material, like graphene, onto a substrate. Then you use a special polymer stamp, often attached to a glass slide, to pick up half of the flake. Then you use a very precise mechanical stage to rotate the substrate relative to the stamp. By the desired angle, we're talking accuracies of 0.1 degrees or even better. Finally, you lower the stamp back down to stack the half it's holding on to the other half, still on the substrate.
Wow, that level of mechanical precision on such tiny flakes, it's hard to picture. Does that method have downsides? You mentioned it enabled the discoveries, but is it practical?
It has huge advantages and significant limitations. The key advantage, especially for homostructures like twisted bilayer graphene, is that you're using two halves of the same original crystal. This gives you an incredibly clean, atomically perfect interface between the layers with minimal contamination. That cleanliness was crucial. That's why it was the enabling technology for the 2018 results. But yes, the downsides. It's very labor-intensive, requires significant skill, and has very low throughput. It's extremely difficult to get uniform twist angles over large areas, like wafer scale, which you'd need for any kind of mass production. Other techniques like chemical vapor deposition, CVD, can grow large areas, but achieving that precise uniform twist angle control with CVD is still a major challenge.
Okay, so assuming you manage to make one of these tiny twisted structures, how do you actually see what's going on? How do you probe these flat bands or weird quantum states?
Right, you need a whole toolkit of pretty advanced experimental techniques. One key tool is scanning tunneling microscopy, or STM, and its cousin, scanning tunneling spectroscopy, STS. STM gives you real space images with atomic resolution. You can literally see the Moiré pattern topography. And STS lets you probe the local electronic density of states. You can map out the band structure locally and directly observe things like the flat bands and the energy gaps opening up in insulating states.
So STM sees it in real space. What about momentum space? That's where bands are usually visualized, right?
Exactly. For that, you need angle-resolved photoemission spectroscopy, or ARPES. It directly maps the electronic band structure energy versus momentum. Getting ARPES to work on these tiny stacked devices was tough, but techniques like nano-ARPES, which uses a very focused beam, were developed. And nano-ARPES provided the first really direct, unambiguous experimental visualization of those predicted flat bands in magic angle graphene, a huge confirmation.
Okay, so you can see the structure in the bands. What about the actual behavior, like insulation or superconductivity?
For that, you rely on quantum transport measurements. You fabricate the twisted structure into a specific shape, usually a Hallbar geometry, with multiple electrical contacts. Then you measure its resistance as you change things like temperature, apply a magnetic field, or vary the electron density using a nearby gate electrode. Insulating states show up as sharp peaks in resistance when you tune the electron density. Superconductivity is unmistakable. the resistance drops abruptly to zero below a critical temperature. And if you see quantized Hall resistance specific resistance values like He, especially without an external magnetic field, that's a smoking gun for those exotic topological states like the quantum anomalous Hall effect.
It really sounds like the twist angle is the master control knob here. It sets the Moiré pattern, which then changes the whole balance between electrons moving around and electrons interacting.
You've nailed it. The twist angle dictates the Moiré potential's period and strength. This, in turn, controls the balance between the electron's kinetic energy, their tendency to hop around, and their Coulomb interaction energy, their mutual repulsion. In most normal metals, kinetic energy wins, electrons zip around. But in these flat band systems created by the twist, kinetic energy gets dramatically suppressed. Suddenly, Coulomb repulsion, which is usually a secondary effect, becomes the dominant player. And that's when all the really interesting, strongly correlated physics emerges.
Right. And that brings us squarely to the big moment. The 2018 experiments on twisted Bel-Air graphene, TBG, that's where this magic angle really hit the headlines.
It really did. As we mentioned, the idea of a magic angle around 1.1 degrees where electron velocity vanishes was predicted by Bistritzer and McDonald in 2011. But theory is one thing. It was the experiments from Pablo Jarrillo Herrero's group at MIT in 2018 that just blew everyone away. Using that precise tear and stack method, they tuned bilayer graphene to near this magic angle, and they saw this absolutely stunning sequence of quantum phases emerge. The material, which you'd expect to just be a metal, suddenly became a correlated insulator at a specific electron density half-filling of the Moiré band. And then even more shockingly, if they doped it slightly away from that insulating state, it became a superconductor.
Okay, let's dive into those flat bands again. This is where it gets really wild, isn't it? You said kinetic energy is almost completely quenched. What does that feel like for an electron?
Well, it's hard to anthropomorphize electrons, but effectively at the magic angle, the complex quantum mechanical interference between the two slightly twisted graphene layers conspires to create these incredibly narrow energy bands right near the energy level where electrons sit, the Fermi energy. Normally, electrons have a wide range of energies available, allowing them to move easily. In a flat band, they're all crammed into a very tight energy window. Their group velocity, how fast electron waves propagate, plummets towards zero. When kinetic energy is suppressed like that, electrons don't want to move much. Their tendency to hop is weakened. And then their mutual repulsion, the Coulomb interaction, which is always there but usually less important than kinetic energy, suddenly becomes the dominant force dictating their behavior. Another consequence of flat bands is a very high density of states. Lots of available quantum states packed into a tiny energy range. This high density makes the system unstable towards forming collective states, like magnetism or superconductivity.
And this first weird state they saw was the Mott-like correlated insulator. Okay, what makes an insulator Mott versus just a regular insulator? And why Mott-like?
Right. A standard insulator, like rubber, doesn't conduct because its electron bands are completely full. There are no empty states for electrons to move into. A Mott insulator is different and stranger. It's insulating even though its electron bands are only partially filled, which, according to simple band theory, means it should conduct. The reason it doesn't is purely down to strong electron repulsion. In magic angle TBG, the flat bands localize the electrons somewhat within the Moiré superlattice sites. If you try to put two electrons on the same site, or nearby, the energy cost due to Coulomb repulsion becomes enormous, much larger than the tiny kinetic energy they have available to hop away, so the electrons effectively get stuck, they forbid each other from moving on to already occupied sites, and the whole system locks up into an insulating state. This is often described using the Hubbard model, where this competition between hopping T and on-site repulsion U is key. Mott insulation happens when U is much larger than T. They observe these insulating states at specific integer fillings of the Moiré bands, for example, when each artificial atom in the Moiré lattice had exactly 2 electrons, or holes.
Okay, so repulsion makes it lock up. But then, superconductivity. How do you go from electrons hating each other so much they won't move to them pairing up and flowing with zero resistance? That seems like the complete opposite.
It does seem contradictory, and that's precisely why it's so fascinating and why it points towards an unconventional mechanism for the superconductivity. When you add or remove just a few electrons, doping the system slightly away from those integer fillings where it's insulating the superconductivity pops up, the material conducts perfectly below a critical temperature, typically around 1 to 3 Kelvin in the initial experiments. And crucially, the phase diagram mapping out temperature versus electron density showed these domes of superconductivity appearing right next to the correlated insulating phases. This is incredibly reminiscent of the phase diagrams of high-temperature cuprate superconductors discovered back in the 80s.
The cuprates,
Yeah.
right. And their superconductivity is still not fully understood, is it? So this resemblance was a huge hint that something weird was going on in the graphene, too.
Exactly. It immediately suggested that the pairing mechanism in magic angle TBG was likely unconventional, meaning not explained by the standard Bardeen-Cooper-Schrieffer BCS theory, which describes most conventional superconductors where electron pairing is mediated by lattice vibrations or phonons.
So what's the actual evidence? What makes researchers confident the superconductivity is unconventional?
There are several strong indicators. First, as we discussed, it emerges directly from doping a correlated insulator, not a simple metal. That's a classic sign. Second, experiments like STS measured the superconducting energy gap, the energy needed to break an electron pair, and found it was anomalously large compared to the transition temperature. The ratio 2 KTC was reported to be huge, maybe 25 or even higher, whereas BCS theory predicts around 3.5. That's a massive discrepancy. Third, there's often evidence of a pseudo-gap phase above TC. This means some characteristics of the superconducting state, like a partial gap in the electronic spectrum, persist even in the normal state above the transition temperature. It's like the electrons are still paired up in some sense, but without the long-range coherence needed for zero resistance. This is another feature shared with the cuprates. And more recently, things like measurements of the superfluid stiffness, which relates to how many electrons are participating in the supercurrent, also show anomalies linked to something called the quantum geometry of the flat bands. The debate about the exact mechanism, is it purely electronic repulsion or maybe electron-phonon coupling enhanced by the flat bands, is still very active.
Wow. Okay, insulators, superconductors, and then there's topology. You mentioned the quantum anomalous Hall effect, QAH. What does it mean for these flat bands to be topologically non-trivial?
Yeah, it gets even weirder. Topologically non-trivial means the quantum mechanical wave functions of the electrons in these flat bands have a kind of global twist or structure in momentum space that can't be smoothly undone. It's mathematically characterized by an integer called the Chern number, C. If a band has a non-zero Chern number, it implies the existence of special states at the edges of the material. The QAH effect is one dramatic consequence. A QAH insulator, or Chern insulator, is insulating in its bulk, just like a regular insulator. But along its edges, it hosts perfectly conducting one-dimensional channels. Electrons can flow along these edges without any resistance in only one direction. This leads to a quantized Hall resistance, Rxi equals HCC, where C is the Chern number. A very precise value, crucially, without needing any external magnetic field. Normally, the quantum Hall effect requires huge magnetic fields.
No magnetic field needed. How does that work? Where does the effect come from then?
It arises from spontaneous symmetry breaking. In TBG, at certain fractional fillings of the Moiré bands, like 34 filling, the strong Coulomb interactions can cause the electrons to spontaneously align their Valley quantum number, or sometimes their spin, to minimize repulsion energy. This spontaneous alignment breaks time reversal symmetry just like an external magnetic field would, and effectively generates an internal magnetic field through the electron's orbital motion. This is sometimes called orbital ferromagnetism. This intrinsic effect is what endows the bands with a non-zero Chern number and leads to the QAH state.
So TBG really is like this amazing playground, a Rosetta Stone almost, for all these complex correlated electron phenomena. And it's not just one magic angle, but a magic range. Plus, you can tune it with strain.
Yeah.
Incredible control.
Absolutely. It opened up this whole new way of thinking about engineering quantum states.
But the story doesn't stop with graphene, right? While TBG lit the fuse, the field quickly moved on to look at twisting these other 2D materials, the TMDs. You said they offer something complementary.
That's right. Twisted TMD bilayers, or heterostructures involving TMDs, provide a really distinct and, in some ways, richer platform compared to graphene. The key differences stem from the intrinsic properties of monolayer TMDs themselves. As we said, they are semiconductors with a direct band gap, unlike graphene. And, very importantly, they have much stronger intrinsic spin-orbit coupling, SOC. This strong SOC leads to that spin valley locking we talked about, which lifts some of the degeneracies present in graphene. This can actually simplify the theoretical picture for certain correlated states and provides a more, let's say, robust pathway to realizing magnetic and topological phases because the necessary ingredients are kind of built in.
Okay, simplification can be good. So what kinds of correlated states do we see in twisted TMDs? Are they similar to the Mott insulators in graphene or something different?
They are conceptually similar, arising from flat bands induced by the Moiré pattern, leading to strong correlation effects. But there's a key quantitative difference. The energy scales are often much larger in twisted TMDs. Correlated insulating states have been observed in various twisted TMD systems, like twisted WS EROs or MOTE, that persist to significantly higher temperatures than in magic angle TBG. We're talking reports well above 150 Kelvin, and in some cases, hints of correlation effects even approaching room temperature.
Wow, 150 K or higher. That's a huge jump from the few Kelvin in TBG. Why the difference?
It's thought to be due to a combination of factors. TMDs generally have smaller dielectric constants than graphene sandwiched in HBN, meaning Coulomb interactions are inherently stronger, less screened. Also, the Moiré potential itself can create larger band gaps in TMDs. These correlated states are often described as generalized Wigner crystals, where electrons localize due to repulsion, forming a crystal structure, or Mott insulators, similar to graphene. And a really nice feature is their tunability. Applying an out-of-plane electric field, the displacement field, can effectively tune the band structure and drive transitions between metallic and insulating states.
And you mentioned TMDs are great with light. Does that play out in the twisted version? Something about Moiré excitons?
Yes, that's probably the most distinctive feature of twisted TMDs compared to graphene. Excitons, these bound electron hole pairs, dominate the optical properties of TMDs. They're how TMDs absorb and emit light. Now, when you create a Moiré superlattice in a twisted TMD bilayer, that Moiré potential we discussed acts as a periodic array of traps for the excitons. Excitons get localized in the potential minima of the Moiré landscape. These trapped Moiré excites have unique properties. Their energy, for example, becomes highly dependent on the twist angle, which controls the depth of the trapping potential. This shows up experimentally as a significant shift, usually a red shift. In the photoluminescent spectrum, the color of light they emit changes with the twist. You can also get different types of Moiré excitons. For instance, interlayer excitons, where the electron is in one layer and the hole in the other, can have very long lifetimes because the charges are separated. At very small twist angles, another effect becomes important too.
You mentioned this before, atomic reconstruction. What's that about? It's not just the layers sliding over each other.
Right. At very small twist angles, typically below about 2 degrees, the assumption that the layers are rigid breaks down. Instead, the atoms within each layer actually displace slightly, rearranging themselves locally to maximize regions of energetically favorable stacking, like AB or BA stacking, and minimize unfavorable regions, like AA stacking. This atomic reconstruction fundamentally reshapes the Moiré potential landscape. It creates sharper domain walls between stacking regions and can significantly deepen the potential wells trapping the excitons. It's a crucial effect that needs to be included in theories to accurately describe experiments at these small angles. The material subtly reconfigures itself.
Fascinating. The material itself is actively participating. And looking ahead, you mentioned predictions of emergent multiferrocity and magnetism in twisted TMDs. What does that entail?
Yeah, this is a really exciting theoretical frontier. Multiferroics are materials that exhibit more than one primary ferroic order simultaneously, like ferromagnetism and ferroelectricity. In some twisted TMD systems, particularly those with inherent magnetic moments or strong correlations, theoretical studies predict that you could get spontaneous multiferroicity. The ferromagnetism might arise from electrons aligning their spin and valley degrees of freedom due to interactions, while ferroelectricity could arise from a spontaneous layer polarization. The really tantalizing prospect here is the potential for electrical control over magnetism or magnetic control over electrical polarization, which could be revolutionary for things like low-power memory and logic devices. The built-in spin valley latching and strong correlations in TMDs makes them a very promising platform to explore these ideas.
So if we sort of step back and compare the two, graphene seems to be the champion for exploring fundamental electron correlation physics, like Mottness and unconventional superconductivity. TMDs bring in the semiconducting aspects, strong light interaction via excitons, and maybe more robust routes to magnetism and topology. That's a pretty good summary, yeah. When you synthesize it, their intrinsic differences really dictate the emergent physics. Graphene, semi-metal, weak SOC, that fourfold spin valley degeneracy, massless electrons, leads to Mott physics, unconventional superconductivity, weaker optical response, interaction-driven topology, TMDs, semiconductor, strong SOC, built-in spin valley locking, massive carriers, prominent excitons, leads to correlated insulators like Wigner crystals, often at higher temperatures, strong optical response dominated by Moiré excitons, and potentially more robust or easily accessible topological and magnetic phases due to the SOC. So the choice of platform really tailors the quantum phase space you get to play in. It's all about picking the right ingredients for the physics you want to engineer. It really does sound like a quantum engineer's dream toolkit. But surely it can't all be smooth sailing. What are the big roadblocks or challenges researchers are grappling with right now in Twistronics?
Oh, absolutely. There are major challenges. Fabrication and scalability are probably the biggest practical hurdles. That tear and stack method, while revolutionary for lab discoveries, is just too slow, low yield, and difficult to control precisely over large areas for any real-world technology. Getting uniform twist angles, minimizing strain variations, avoiding contamination, doing all that reliably on a wafer scale, that's a huge materials science challenge. Current methods like CVD just don't have the required angular precision yet.
Okay, so making them is tough. What about understanding them?
That's the other side of the coin. Theoretical complexity. Remember that Moiré unit cell with 10,000 atoms? Doing exact quantum mechanical simulations on systems that large is computationally prohibitive, even with supercomputers. So theorists rely on developing effective models like the Bistritzer-McDonald continuum model, but finding models that are both accurate and computationally tractable, especially when strong correlations are involved, is really difficult. We need better theoretical tools. And tied to that is understanding the fundamental mechanisms. Even for magic angle graphene, the precise pairing mechanism driving the superconductivity is still hotly debated. Is it purely electronic? Is it phonon-mediated but strongly enhanced by correlations? Nailing down these fundamental questions is crucial.
Challenges, yes, but they sound the kind that drive innovation. So looking past the hurdles, what are the really exciting future directions? Where could Twistronics take us?
The potential is enormous. One big area is quantum simulation. Because you can tune the interactions and band structure so precisely with twist angle and gating, these Moiré systems offer an unprecedented platform to experimentally realize and study fundamental theoretical models of condensed matter physics, like the Hubbard model we mentioned, or models for quantum magnetism. It's like building a tunable quantum sandbox.
Simulating quantum physics with quantum materials. Neat. What about more applied areas? Computing, electronics.
Definitely. For quantum computing, the ability to engineer topological phases like those QAH churn insulators is very attractive. Topological quantum bits, or qubits, are predicted to be inherently more robust against errors, offering a path towards fault-tolerant quantum computation. Moiré materials could provide a new way to create and control these topological states. And for more conventional or perhaps unconventional electronics and optoelectronics, the possibilities are vast. Think about those electrically switchable insulating, superconducting, or magnetic states. They could form the basis for entirely new types of transistors, memory elements, or reconfigurable circuits where you change the device function on the fly. In TMDs specifically, that fine control over more excitons is really exciting for optoelectronics. Tunable single-photon emitters for quantum communication, perhaps ultra-low threshold lasers, maybe components for integrated quantum optical networks, all potentially enabled by engineering light-matter interactions at the nanoscale using twist angle.
It feels like the trajectory is towards even greater complexity and control. People are already looking at twisted trilayers, quadrilayers, twisting different combinations of materials, incorporating 2D magnets or ferroelectrics into the stacks.
Exactly. And developing new experimental tools like using microelectromechanical systems, MEMS, to apply strain or even continuously change the twist angle in situ on a single device, that takes the designer quantum material idea to a whole new level of dynamic control. The field is moving incredibly fast.
So let's wrap up this deep dive on Twistronics. It's pretty amazing, isn't it, how just taking these atomically thin sheets and giving them a little twist opens up this entire universe of quantum phenomena. We've seen correlated insulators, unconventional superconductivity, these weird Moiré excitons, hints of topology and magnetism, all unlocked by geometry. It truly embodies this idea of designer quantum materials.
It really does. It's a beautiful example of how fundamental physics discoveries, understanding electron behavior in these unique structures, merge with advanced materials engineering, actually building them layer by layer, atom by atom, with precise control. The synergy is powerful.
So here's a thought to leave you with. Think about that simple mechanical action, a twist, something we do every day without a second thought. Yet, applying it at this nanoscale level completely revolutionizes our ability to understand and control matter at its most fundamental quantum level. It makes you wonder what other simple, maybe overlooked physical actions or geometric arrangements might hold the keys to unlocking equally profound shifts in completely different fields, maybe fields that seem totally unrelated. Definitely something to ponder. Thanks for joining us on this deep dive into the fascinating world of Twistronics.